Okay, so we're going to focus on finding out when y is concave up, and I'm focusing on the justifying piece first. Well, what do I need to know? If this function is concave up, then its second derivative has to be positive, or we say it's greater than 0. That's all you need for the justification piece, is this piece written in orange. Why is it concave down? Well, it's going to be concave down when the second derivative is negative. What that means is I have to take the first and second derivative of my answer. So I'm going to do that over here. I'm going to deal with the first derivative. And if you would like, you can show your work, but you notice that this is a product. So we have two pieces. We've got u and we have v. If you would like to show this work, you can. I'm hoping you can kind of do this part in your head so you can avoid showing all this work. Because the derivative of x is 1, the derivative of e to the x is e to the x. And now we can set up our product rule. It's the derivative of the first term times the original second, plus the original first term times the derivative of the second. Right, so there's my first derivative. But I don't really need to even look at anything within that first derivative if all I'm focusing on is concave up or concave down. So now I have to take the derivative of the derivative, and you'll notice technically I really don't even need this 1 here because 1 times e to the x is just e to the x. So the derivative of the first part, e to the x, is just e to the x. But then I have another product rule. I've got x times e to the x, which notice that's the same thing as the original function. So I don't need to redo my work. I'm just going to use the same stuff that I have up here. Or if you think of it, it's really just this answer written again. But it's the first term times e to the x. So 1 times e to the x is just e to the x. And then it's x times e to the x. And there is my second derivative. Right? So now we have to actually set that equal to 0. So I'm going to take the concavity is where the second derivative is. We got to find the potential inflection point. So we're actually doing some of the work for number 2 as well right here. And what I'm going to do is I'm going to actually factor this. If you'll notice, well, actually, we can combine these two like terms. I have 1 e to the x here and 1 e to the x here. So if I add them together, I have 2 e to the x's plus an x e to the x. But then both of these terms actually have an e to the x in common. So we're going to factor out an e to the x away from each piece. And that's what allows us to get to this zero product property that says each factor has to equal its own 0. Okay? Now there's a couple ways to think of solving this one here. If you just understand that the graph of e to the x, the graph of e to the x looks like this. It's an exponential growth function. It's never, ever going to cross 0. And since this graph will never equal 0, this part right here is not going to give us an answer. We can't solve this. There is no x value that makes this true. So our 0, or I should say our inflection point, is not going to be in this first part. Now, the second part, that's pretty quick to solve. We get, subtract the 2 over, I get x equals -2. All right? Now, that's a potential inflection point. So that's actually could be part of the answer to number 2. But what we need to do is we need to check the sign chart for the second derivative because I want to know where the second derivative is positive or negative. And we know that it's 0 at x equals -2. So I'm going to label my sign chart as y prime. And then this is where you really got to be a quick way to do this is we got to test the point here. I'm going to test -3. You can test anything less than -2. But notice, if I plug in anything, any x value into e to the x, that will always be a positive answer. Part of it is because of the graph, right? So I don't ever have to worry about the sign of e to the x, which means when I test my values, the only thing I'm testing is this factor 2 plus x. And if I plug in -3 here, I'll get a -1. So a negative times a positive means it's negative. The second derivative is negative to the left of 2. And then I'm going to test a number past -2. I'm going to test 0 because that's pretty easy. Again, this first part is always going to be positive. Even if I put in 0, e to the 0 is 1, and that's a positive. If I put in 0 here, I get a positive again, and a positive times a positive is a positive. Okay, so we now have the information that we need. When is y concave up? Whenever the second derivative is positive. So I'm going to have to make a connection here. And then whenever the second derivative is negative, y will be concave down. So one of the things we have to really work on is our justification or our answer to these problems. How do we actually write this out? Because this would not be good enough. Okay, the people on AP tests, when they read your responses, they're told not to read the sign chart because they want students to justify. So we're going to say y is concave up on the interval from -2 all the way to infinity. That's the positive part. And then all we have to do to justify is say because y double prime is greater than 0. That tells me why it's concave up. All right, so then when is y concave down? From -infinity all the way to -2. Notice they're soft brackets because actually at -2 it's equal to 0, which means it's a point of inflection. And then our reason why it's concave down is because y double prime is negative. Notice how I did not use the word it. It is not concave up. We want to be specific. You always want to make reference to the original function. In this case, it was y. All right, so don't use the word it or they or even the graph or the function. Call it by its name. All right, and then we're almost done. Remember what a point of inflection is. Okay, a point of inflection is where the second derivative is equal to 0 or the second derivative does not exist. Now, we don't have an example in this case where it does not exist, but we just showed where it's equal to 0. Now, we also have to be careful because there also has to be a sign change in the second derivative. So notice right here at -2, I go from concave down to concave up, and that's what points of inflections are. They're spots where we change concavity. So my answer is, should start off with the function. Y has a point of inflection at, and notice what they told us. They want the XY combo. So we know where it's occurring at the X value. What I then have to do is I have to find that Y value. And this is, notice, XY. Y is the original function. So I just got to go back up to the original function, and I got to plug in -2. So -2 e to the negative 2, which if this was a multiple choice answer, this would be completely acceptable, but if it was multiple choice, they would rewrite it with that negative in the denominator. And notice how I didn't grab my calculator, right? It's actually, if you grab your calculator, you're rounding at some point, and it is not as accurate. And we want to avoid rounding whenever we can. Okay, so that was the warm up. You definitely expect a question similar to this on the test on Friday. Okay. All right. If you are interested, you would have to email Miss Myers or Miss Tierra today to get the information so you're ready for tomorrow. But Black History Month is looking for student leaders to help plan and organize the second annual Black History Month showcase. You must be able to attend meetings at 3 o'clock starting on Thursday, December 17th. I'm assuming they're probably going to always be on Thursday. Have a passion for unity and community. Check your emails daily. There's a link that you can follow. You should have gotten an email from Miss Myers or Miss Tierra on this, but you would have to fill that out by tomorrow. And then the meeting is Thursday. The first meeting is Thursday. If you got any questions, email Miss Myers or Miss Tierra. Okay, we have to really talk about this last quiz on AP Classroom, and I'll share with you how I graded it and what we're going to do with it. All right, so what do we want to look at really quick is we've got, if I'm given a graph, now that graph could be an f, f prime, f double prime. It says it's twice differentiable. So let's just talk about what that means. That just means the derivative exists twice. So that means that the function is fully continuous on the interval. In this case, it's the open interval, so the endpoints aren't part of it. And then they tell us that we have points of inflection at each one of these values. And they have small little green circles. So these green circles are the spots where we change concavity. I know that because of the definition of point of inflection. So that actually helps me identify pieces of the second derivative. Okay? Now, what they're asking us to do is they're saying focus on the point x equals 1. And tell me, what do you know about the point, the first derivative, and the second derivative? But before you answer this question, you got to know what graph you're looking at. This is the graph of the original function. So what I'm going to do is I'm going to go over to 1. So here's 1. I'm looking at this point. And what do I know about f of f of 1? Well, f of 1, we actually know the exact output. It is -7. So I'm going to go down here, and I just have to, if I click on the menu, it'll give me 3 options. Well, f of 1 is negative, so it's less than 0. All right, so that would be my first answer. And then you actually have to interpret, what are they asking for when they say f prime of 1? Well, that is the slope of the original graph. So I have to go here and I have to now look at the slope of the tangent line at that point. Well, it's a minimum, and every minimum is going to have a horizontal slope. So the slope at 1 is equal to 0. All right, and then we're looking for the second derivative, and this is the spot where we're looking for concavity, right? So what do we know about the shape of the graph right around this point at 1? Well, notice this is concave up from right here. So if it's concave up and at x equals 1, that's part of it. Well, concave up is referring to the second derivative has to be positive. So we can make conclusions based off of what's happening at that point. So you're going to have to go through and practice that today. And I think that one's pretty decent. This one is another question that you're going to have to go through and ask. or answer. But notice, what do they give me? Now they give me the graph of f prime. The derivative of the function is shown below. Determine all of the intervals on which f double prime is greater than 0. Well, what does that mean? What we're looking for is, now we have to be super careful here. We're looking for when is f of x concave up. But I don't have the graph of f. I have the graph of f prime. So I have to kind of think of, well, wait a minute, what does it mean about the first derivative if f is concave up? So if f is concave up, that means that my derivative has to be increasing. And we're going to talk more about that today, but that was one of the definitions we used for defining concavity. So I need to look for, when is the graph of f prime increasing? Another way to say that is, when does it have positive slopes? So let's start here. Notice I have negative slopes. I'm decreasing, 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 and then I've got a slope of 0 right here. So I might, and then if we go to the right of that, now notice the tangent lines here are positive. Increasing, increasing, and then all of a sudden I have a slope of 0. Well, in this case, if I have increasing slopes and I'm looking at the graph of f prime, the slopes of this graph is f double prime, and they're increasing or growing. And then we go decreasing until we get to another 0 slope, but then all of a sudden we start increasing again until that endpoint. So there are two spots or two intervals. If I was going to answer this question, we are increasing from -4 all the way to 1, and from 3 up until 9. So at these intervals, f of x would be considered positive, or f double prime of x is positive. Okay, we'll work through that more today, but those are the two things we just didn't get to. All right, so our goal today is to obtain information about the original graph of f, given the graphs of f prime and f double prime. Today's a pretty heavy day, so hopefully you are fully engaged and paying attention. And actually, what I'm going to do right now is I'm going to just quick throw you in a breakout room. And all it is I want to check to see who's fully engaged and who might be not paying attention. And those who aren't paying attention will get, all right. Now we're going to start off. I don't want you to write this. This is just setting the stage. Okay? This is just setting the stage for where we're headed. So don't write this. We're going to go over it super quick. But it's kind of where we've been. So the graph shows the position of a particle moving along a line. So the position function is given by s of t. Every once in a while they call it x of t. You can even call it y or f of x. It doesn't matter. But this is the graph of the original function. Right? When is the particle's velocity equal to 0? So another way to ask this is, when is the particle stopped? Right? If it's equal to 0, the particle is stopped. Well, what has to be true then is the velocity, which is equal to the derivative of the original function, has to be equal to 0. And what we're doing is we're checking the slopes. And where are the slopes equal to 0? Well, here, the derivative is 0. Here, and here. So we've got 3 spots, and if I was going to answer this, I would have to say it's at t equals maybe 2.75, t equals 6, and t equals maybe 9.25. Right? Now, if they ask me to justify, here's my justification. How do I know that velocity is equal to 0? It's whenever the derivative is equal to 0. You should say So you should say that v of t is equal to the derivative of the function, because you always want to make a connection to what velocity is to the graph that's given. All right, now look at the next one. It says, when is the particle's acceleration equal to zero? So what do I have to do? I have to say, well, if it's acceleration is the second derivative of this function, and I want to figure out when that's equal to zero. Well, that's at the spot where there's a change in concavity. Okay? This is what we talked about on Thursday. So let's take a look at what do we know. I am concave down on this yellow part, and I'm also concave down here. Those are the two spots where we're concave down, concave up on the blue part. But notice that little green overlap. Those are the spots. And if this was like an AP question, it would be more detailed, so you wouldn't be guessing. They would have a little dot right here, and they'd have a dot here. All right, so where does the acceleration equal zero? This is at points of inflection. All right, and those are at t equals maybe 4.15, I'm guessing on that, and this might be 7.5. Okay, so why did I show you this? Well, some students do a whole lot better when they think of the graphs in terms of particle motion. Instead of just here's F, and here's F prime, and here's F double prime, if they apply an actual motion to it, that could be helpful. All right, so this is what I would like you to write down. We're going to answer these 4 questions based off of the given graph, and we're going to change the graph each time. So first we're going to say, okay, well, what happens if it's F prime? Or F, excuse me, the graph of F. And then what happens if I give you F prime and F double prime? So I'm going to give you a minute to write this down. Okay. So when we're doing problems like this, it is super important for you to fully understand what this graph is. And it's usually going to be labeled. Now here they tell us exactly what it is in the directions, and they'll usually do that, but they might also just put f of x right next to the function so you know. Now we do have to have a couple of kind of points that we're all agreeing on. So I'm going to just say that this is the point, negative 2.5 up, let's say up 7. So that's the maximum. The minimum is at the spot negative 3 comma 0. All right, and then here this 0 is at the point negative 2 comma 0. All right, so here's what I like to do when I have problems like this. If they tell me to find the critical points, the very first thing I do is I just, without even looking at the graph, I think, all right, what do I know about critical points? They are where the derivative is equal to 0 or does not exist. And then there has to be a sign change as well. Let's just leave that out. So where does the derivative equal 0? Well, if I look at my graph, I'm looking for the slopes. I'm looking for f prime, and this is the graph of f. So f prime is the slopes of this graph. And critical points are at the maximums and minimums. So here's where f prime of x is equal to 0. And you don't need to write all this stuff on your graph, but we know that at negative 2.5 and negative 3, those are going, oh, that should be a positive 3, sorry, not a negative. That's on the positive side. There we go. All right, so if I asked you to just answer the question, you would put these, if I asked you to justify, then you would have to write the explanation. My recommendation is write them both until you've absolutely 100% memorized them. Okay. Part B, find the inflection points of f. Well, what do I need to know about the inflection points? That's where the second derivative is equal to 0 or does not exist. Plus, there's a sign change. Now, another way for us to think of this is this is the point where we change concavity. That's what inflection points are. So this is actually going to kind of help me answer the rest of the questions too. Let's look at this function and look where it's concave down. It's opening downward wherever I highlighted in yellow. And then wherever I highlight in blue, it's opening upward. So it's concave up. Well, inflection points are the spot at which it changes concavity, and that is right there, that overlap. Now, again, this is not the perfect graph. They would give you the location of this point so you wouldn't have to guess, but it's usually safe to say that it's exactly halfway between the max and the min. But again, it'll be more specific. So if I take halfway, I believe this is like 1.25 roughly. That's not necessarily true, but let's just call this the point 1.25. So there is a change in concavity at x equals 1.25 because my second derivative, changes signs there from negative to positive. And then the nice thing is by checking for the inflection points, you also know where the concavity is. So where we concave up from the inflection point all the way to infinity, that's the blue highlighted piece. And then when are we concave down? From negative infinity to the inflection point. Okay, so the way we find these, the thought process doesn't change. We have to change our thinking with how we view the graph. So in this problem, we are given the graph of f prime. You could think of this is the graph of the velocity function because it's the derivative. So if I want to find the critical points, we know that critical points occur when the derivative is equal to 0 or does not exist, and there's basically two of them. Right? Now we have to think, well, what does this mean? When the derivative is equal to 0, by the way, there are no spots where this derivative doesn't exist because this is a continuous graph. So we don't have to worry about the do not exist part. But if I look at these two orange spots, those are the spots where the derivative is equal to 0. I did it again. This should be a positive 3. I don't know why I want to keep putting that negative. There we go. Okay. So our thinking doesn't change for the meaning, but we have to just interpret the graph differently. Now I have to look for inflection points. Okay, well, what are inflection points? Inflection points are where the second derivative is equal to 0 or does not exist, and then there's a change of sign. Weird looking. So let's think of this. Now I have the graph of f prime. If I have the graph of f prime, then f double prime of x is the slopes of f prime. So I have to look at, do I have any slopes on this graph that are either 0 or spots where it's undefined? And again, there is no spots where it's undefined. So where do I have 0 slopes? Well, here the slope of f prime is equal to 0 because that's a maximum. And here the slope of f prime is equal to 0 because it's a minimum. So I've got two spots at which my original graph will have an inflection point. Now, how do we deal with that sign change? Well, let's look at this. Leading up to this 0 slope right here, my slopes are positive. Right? I've got positive slopes, and then they become negative. So there's a sign change. And then my slopes are negative, negative, negative. So I've got negative slopes here. But then right at this point, it's 0. And then past that, the slopes start to become positive. So I'm checking the sign change as well. Now, why is that important? Because I can then quickly identify when is the second derivative greater than 0. Well, that is the concavity. Right? It's concave up wherever I have positive slopes because f double prime is the slopes of f prime. So you have to be super careful. Where do I have positive slopes? Those are going to be in yellow. And actually, I think, you know what, I might have done blue. So let me change that. Doesn't really matter. Concave up are wherever I have positive slopes. So if you look at this graph, f prime has positive slopes leading up to the maximum, and then it has negative slopes, and then we're increasing again. So there's another way to think of this. Concavity is also when f prime is increasing, and those are those blue highlighted spots where f prime is increasing. So we're increasing from negative infinity to negative 0.25. And if it was delta math, they'd put the little union symbol. And then we're also increasing from 3 to positive infinity. Okay. Well, where is f concave down? Concave down when the derivative has negative slopes. Right there, right there. All right. Another way to confirm the answer to part B is if I know where the interval is concave up and concave down, points of inflection occur when we change from concave up to concave down or vice versa. And those are the two green spots, which notice those are what we call the points of inflection. I don't know if you want to write this part, but sometimes students do better looking at a sign chart with certain pieces. Because notice, I didn't ask you when the function was increasing or decreasing. I didn't ask you if there was a maximum or minimum yet. But let's look at what we could do here based off of this sign chart. Okay, notice at -2 and 3, I've got critical points. And that's what we answered for this problem. But then I notice that f prime of x is negative anytime it's below the x-axis. So I've got a negative f prime right here. And then after that, it's always above or equal to 0, so it's positive, positive. So if you make a sign chart from this, notice what happens. I have decreasing slopes, and then I go to increasing slopes. Well, wait a minute. Decreasing to increasing tells me that the original function has a minimum at -2. And I didn't ask you that, but you could totally find that. And then here we go from increasing slopes to increasing slopes, which means there's no sign change. So that's a flat spot on the original graph. So some students like this, is if you make your graph, you can make a sign chart and it can kind of help you answer these questions. If I wanted to, I could make a sign chart for f double prime as well. So f double prime, where does it change concavity? At the 2 points of inflection. So actually, I try to put this in a little bit of order. I know that the blue interval is where we're concave up. So the second derivative would be positive because we're increasing all the way to the point of inflection. And then it's decreasing, the yellow highlighted, and then it goes to increasing. So you can see the points of inflection here. And now we know the intervals where the original function would be concave up, concave down, concave up. And we could also compare that to where the intervals would be increasing as well. So a sign chart is something you could make if it helps you. All right, we got one last slide that you guys are going to write down. And this one, I just switched it up. I didn't go with the same graph. I just went with a different graph. But we're going to see if we can answer the same points given the graph of f double prime. And make a real rough sketch for this graph. It does not have to be accurate. Okay, all we're going to do is we'll identify just the key points. So 1, 2, 3, 4, 5, 6. Just call that -6, 0. That's -2, 0. And then this one has a little flat spot at 3. And those are the only spots you need to know. We're going to see if we can answer the same questions based off of this graph. Okay, so here's the key. When you have the second derivative graph, it's really hard to go backwards to figure out information about the very original graph. So for me to figure out information about f in terms of critical points is I really don't know when the original derivative would have been 0 or potentially does not exist. So If you're ever asked to go back to find maxes, mins, when something is increasing or decreasing on the original function, even critical points, um, we can just say no conclusions can be made. And I'll just ease your mind. We're not going to try to trick you on points like this. All right? But what can you conclude from the second derivative? You can conclude where points of inflection occur, because that's where f double prime of x equals 0 or does not exist, plus the sign change. That's not too horrible to figure out. Okay? Where do points of inflection occur? When the second derivative is equal to 0. Well, this is the graph of the second derivative. So where does it equal 0? At 3 spots. So this is just basically strictly reading the graph. So at x equals -6, -2, and 3. Those are the spots where the second derivative is equal to 0, because this is the graph of the second derivative. All right. Where is f concave up? So my brain is thinking f is concave up when the second derivative is positive. So now I'm looking at, this is the graph of the second derivative, and I want to figure out when it's positive, and that's anytime it's above the x-axis. So the intervals would be anything above -6 to -2, unioned with anything from 3 on up. And some students like the highlighting piece. So I know that the original graph is concave up anytime the second derivative is positive. And then where is it going to be concave down? Whenever the second derivative ends up being negative, which is below the x-axis this time. So anything below the x-axis, second derivative is less than 0. And that's from -infinity to -6, unioned with the piece from -2 to 3. So, in general, if you're given the graph of f double prime, you can really only determine when the original function is concave up, concave down, or has inflection points. If you're given the graph of the first derivative, that's the one where you can determine everything. All right, I'm going to just show you this. I'm not even going to explain it. This was another example. We definitely don't have time for this. But if you want to, I'm going to have this revealed. It's kind of another piece just like we looked at. But it's basically, here's the graph of f double prime. What can we conclude and why, based off of this example? And then here's the graph of f prime. What can we conclude? Look at all those things. Okay. And then what would the graph, we aren't even going to get to that piece. But you'll be able to go back and look at this if you would like, if you just needed another example. And then I wanted to show you these quick that I knew you weren't going to write. But let me show you one case here that if you have a graph, and I know we only have a couple minutes left, so watch what I'm going to do. I'm going to make a sign chart. to make this a little easier to view. Now, this is the graph of the derivative. So I'm going to label the spots where the derivative is equal to 0 right here. All right, and then what do we know? The derivative is above the x-axis, so it's a positive slope from -2 to, now here we have to be careful. This is kind of interesting. We still have a positive values here. So that means this would definitely be a flat spot, right? You can see that's a flat spot. And then this goes from positive slopes to negative slopes. So in the original graph, I go from increasing to decreasing. There'd be a maximum here. So we know where the slope is increasing and then where it's decreasing. But we can also make a sign chart based off of f double prime. All right, now notice, what do we know about the slopes? The slopes here, if I drew the slopes are all negative until I get to 0. At 0, I have a 0 slope, so my slopes were negative, and then they go to positive. But right here at x equals 1, the derivative does not exist right here. It's an open circle. So that's still a critical point because my slopes are positive, 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 positive slopes, and then they go negative, negative, negative. There's a sign change. And then they're negative all the way throughout. So what do I know? I know that when the second derivative is negative, this is concave down, this would be concave up, and this would be concave down, and I would have 2 points of inflection because it's ones where the derivative or the slope of the slopes is 0, or the derivative doesn't exist. So we can determine, I know the original graph is increasing if its first derivative is positive, and then it would be decreasing. But I also know concavity based off of this graph. So just making a sign chart sometimes can make this a little easier. And then the last one I don't want you to write down is if you have a table is basically the same thing as a graph, except for you can only make the conclusions of what the table says. So watch what happens if I make a sign chart here. So what I want to do is I want to look for when does the derivative equal 0. It equals 0 at 2 spots. So I'm going to say at x equals 0, and then it does not exist. But we also know the slopes to the left of 0. The slopes to the left of 0 are positive. The slopes between 0 and 3 are positive, and the slopes past those points are negative. So I can determine when the original function is increasing, and there would be a maximum here because I go from increasing to decreasing, but the slope doesn't exist. So this might be a corner because your graph's going to be going up and then it's going to be going down, but the derivative doesn't exist, so it doesn't mean it's a smooth curve. It might just be a sharp corner, or it could be discontinuity. We don't really know. We would need more information there. All right, but now look at the second derivative. The second derivative also has a 0 at x equals 0, and it went from being negative to positive. So this point right here is a point of inflection, because there's a change in the second derivative. And then at x equals 3, it doesn't exist, but I go from positive to positive, so there is no sign change, which doesn't make this a point of inflection. So I just wanted to show you that quick. Sign charts can be helpful. All right, we're going to skip those. So here's what you got. Homework tonight is to finish last Friday's 5.3 day 1. And on Wednesday, this should have said Wednesday, there is no video to watch today, but on Wednesday, your work is going to be just to watch a video. That's all I got. I'll be in my office hours today from 1 to 2. Stop in if you need any help.